Imagine building a finance app where roommates can easily split a dinner bill. In the beginning, linking two accounts together is seamless, but as the app starts to scale globally, millions of users are suddenly forming complex webs of shared expenses, split checks, and group trips. Keeping track of who is connected to who within these massive networks is a classic computer science challenge, known as the dynamic connectivity problem. To solve it, your backend servers have to constantly execute two specific commands. First is find, asking if user A and user B are already in the same payment group. Second is union, which merges their separate groups together. At a global scale, these two commands rarely happen in isolation. Your servers are bombarded with billions of find and union requests every single second. If your algorithm takes even a fraction of a millisecond too long to process a single request, that tiny delay multiplies across the entire network. The application will freeze entirely under the weight of its own traffic. The most obvious way to code this is an approach called quick union. Here, every time a new user joins a group, they simply point their account directly to the specific person who invited them. Over time, this creates a distinct physical shape in your server's memory. Instead of a balanced web, you get a degenerated vertical chain of users, all stacked single file. This introduces a significant flaw. When the system needs to verify which group the newest user belongs to, it has to walk up the entire length of that chain, one length at a time, until it finally reaches the root boss at the very top. This naive structure forces your server to do an amount of work directly proportional to the number of users, a time complexity known as O of n. Simple code logic can create severe physical bottlenecks in the data structure, capping the growth of the entire application. We can address this bottleneck by introducing an optimization called path compression. The mechanic is highly efficient. While the system is already doing the work of walking up the chain to find a user's root boss, it takes a moment to update the user's connection to point directly to that boss, permanently shortening the trip for any future searches. This recursive code executes that rewiring process during every search, specifically this line, where parent of X is reassigned to the result of the find operation. By calling itself recursively, this function flattens out those inefficient vertical chains, compressing them into wider, shallower shapes. But there is a catch. Path compression is a bottom-up fix. It only repairs bad structures after they have already been created. If your incoming data is arranged poorly from the start, the system can still be forced into a bottleneck, degrading to an O of log n worst-case time complexity. Optimizing the search path helps, but to achieve true scale, the system must also optimize how these groups are merged together in the first place. This requires a second heuristic to run alongside path compression, known as union by size. The rule is simple. The algorithm tracks the size of each group and always attaches the root of the smaller group directly under the root of the larger one. This top-down rule prevents the formation of long single-file chains during the merge process. These two optimizations complement each other. Union by size enforces short trees from the top down, while path compression pulls the nodes horizontally toward the root during every search. By addressing the structure during both the merge and the search, the algorithm ensures the data remains compact regardless of how chaotic the input sequence becomes. When you combine these two heuristics, the resulting time complexity drops to O of alpha n, a value determined by the inverse Ackermann function. In mathematics, the standard Ackermann function grows so aggressively that it pushes the limits of theoretical computation, hitting astronomical figures almost immediately. But because the original grows so fast, its inverse grows unbelievably slowly. To put that scale into perspective, even if n was equal to the number of atoms in the physical universe, the output of the inverse Ackermann function would still be less than 5. For our finance app, that means the backend servers can group and sort millions of users in essentially O of 1, constant time. It is practically instantaneous, regardless of the scale. Reaching this mathematical limit is the result of applying logic to both the top and bottom of the data tree simultaneously. Check the GitHub for the full implementation and subscribe for more deep dives into the logic of scale.